Let's get started. So this week's speaker is Abbas and Stefan, and they'll be talking about biomedical imaging and diagnostics. Without further ado, I'll hand the mic.
So, hi, everyone. Everyone can hear me? Okay, all right. So as Professor Carp and I were putting these slides together, I took the executive decision to rename our presentation from Intro to Biomedical Optics to Intro to Biomedical Imaging and Diagnostics. And that will become clear after we actually tried defining biomedical optics. So jump the gun. To start with, we'll give a nice definition of optics, a branch of physics that examines the behavior and properties of light and the interaction of light with matter. Extending that to biomedical optics, you can formally define it as the design and application of advanced optical techniques to solve pressing problems in medicine biology. So in essence, it's just exploiting various interactions between light and biological tissue to try and understand and move forward critical issues with in medicine and biological applications. So very broadly, I like to lump all sorts of applications related to biomedical optics into two different categories. The first of which, photomedicine broadly, it encompasses using light to elicit some sort of actual change in the biological microenvironment. So oftentimes this is used for some sort of therapeutic application. Examples include LASIK and laser treatment of cutaneous lesions in dermatology. In cancer treatment, photodynamic therapy has taken off quite a bit. And there's burgeoning fields where you can use a laser to actually stimulate neural activity or some sort of therapeutic response. And the other category is more imaging and diagnostics, and the goal there is to actually use light to sort of interrogate the environment, but not without actually inducing some sort of change. So it's less disruptive, for lack of a better word, to the microenvironment. There's profound advancements taking place in both of these categories right now, but just for the sake of brevity, we're going to narrow it down just to imaging and diagnostics, which is really our specialties here in the Martinos Center. So I'm going to go over more of the preclinical aspects of biomedical imaging, where we use light in various ways to figure out aspects on both a mesoscopic and microscopic level of samples that are either representative or simple cellular environments that don't encompass like a whole live human, or we'll talk about small animal imaging. And then the later part of the lecture, I'll hand it off to Stefan, so he can talk about more clinically translatable methods. So I'll jump the gun here and just first tell you the preclinical imaging methods, the selling points and the potential drawbacks. What makes it very useful is the fact that in terms of, for imaging and diagnostics, they have pretty much superior resolution over other imaging modalities, other non-invasive or minimally invasive imaging modalities, that is. They're also very versatile. You can characterize multiple features at the same time at the cellular and subcellular level. Also aspects of microvascular hemodynamics, along with several other things that are of strong interest to cell biologists and tumor biologists and neuroscientists. It's also safe, minimally invasive. It doesn't involve carcinogenic or radioactive reagents, so that makes it highly desirable. And also, in terms of hardware, the materials that you can use are relatively cheaper than other modalities, but an order of magnitude or so cheaper, but it still could come, the price could range between a few tens of hundreds of dollars to hundreds of thousands and possibly millions of dollars. It's still cheaper than a lot of the high-end translational equipment that we have today for other modalities, but so yeah, cheap is relative. Can't tell the whole story without actually emphasizing some of the limitations for the preclinical methods that we have right now. The first is particularly for the type of research that I do. It is moderately invasive. It's not easy to bring microscopic methods to the bedside for a human being. Also, it's you can't really image very deep within tissue. It's confined within the first few hundred microns to maybe 1 or 2 millimeters in tissue. So that limits the amount of applications that you have for it. There are advancements being made by use of endoscopic techniques, but that's still in development right now. So in a nutshell, there are certain limitations that keep it from being widely adopted for human brain imaging or other clinical applications. Nevertheless, it's been profoundly useful for understanding a lot at the cellular and subcellular level, and so that's the driving force for a lot of the work that we're continuing to advance today. Now I'll take a step back and talk a little bit about light itself, since we're starting from scratch here. Just to get everyone on the same page, light represents one type of electromagnetic radiation, meaning that it's comprised of oscillating electrical and magnetic fields, which are orthogonal to one another and orthogonal to their propagating direction. Light actually encompasses a rather relatively narrow region of the electromagnetic spectrum. There are a whole bunch of other ones, X-rays to long radio waves. Each of these, several of these have been exploited for different medical imaging technologies. Light falls somewhere in the middle in terms of the frequency bands, the wavelength regions that you use, and the amount of energy that comes with it. So it's also very useful to recall from our high school physics days that light or electromagnetic radiation has both wave-like and particle-like behavior. There's also a very well-defined relationship between the wavelength and the frequency of the type of radiation that you're working with. They're inversely proportional to one another. That's why you have increasing wavelength going in this direction and decreasing frequency in that same direction. And then their product is equivalent to the speed of light in the medium that they're propagating through. If you consider the particle-like nature of light, the fundamental unit of a light would be a photon, and it has a very well-defined amount of energy that's proportional to the frequency of the photon. The constant of proportionality is Planck's constant, and so the energy is also inversely proportional to the wavelength. So this will become important in subsequent slides. All right. Moving on, there's a number of different ways that which light can interact with matter. This is the illustration here on the left actually just describes a certain percentage of them. This is most of them, I would say. Each one of these interactions can tell you quite a bit of information about the matter that the light is interacting with. These top three, they rely on, or they can be best explained by the wave-like nature of light, and the bottom three it could be better explained by the particle-like nature in terms of photons propagating within tissue. So transmission basically is the light that's left over after these processes, scattering and absorption, have taken place, and that's the amount that comes out. Importantly, the basis for most of the medical imaging applications that we'll talk about today are basically predicated on these two interactions: scattering and absorption, and the subsequent luminescence that occurs with certain types of matter, or I'll start calling them chromophores, by which I'm referring to different constituents in biological tissue, or potentially contrast agents. This figure here on the right actually shows, illustrates another very, very important aspect, and that's the fact that the wavelength of light actually determines to a high degree how the extent of which the matter and light will interact with one another. So there's a wavelength dependency on the level at which it happens. What this depicts specifically is the absorption coefficient of different molecules that you'll find in tissue, different, again, chromophores or tissue constituents. Importantly, water as the most prevalent component of biological tissue, its absorption actually dictates to a great extent the range of wavelengths that we can use, because there's only a certain range for which absorption is minimized, and so that allows you to be able to send light deeper into tissue. We call that the optical window or the water window. It's reasonable for well, the range of wavelength that we call visible light. That's from approximately 400 to 700 nanometers, but it's actually more also reduced in the region, the near infrared region, ranging from about 700 nanometers to maybe 1.7 microns, 1700 nanometers. So we can take advantage of those wavelengths specifically to penetrate deep within tissue and get a lot of information depending on which modality that we use. So yes, so again, water is the primary constituent that determines how deep we can penetrate within tissue. Another important feature here that I'd like to emphasize is for a number of different biomedical applications, the two chromophores that are primarily of interest are oxyhemoglobin and deoxyhemoglobin. Just the fact that they have different colors and different absorption spectra has enabled quite a bit of characterization for different medical applications. That should be well illustrated by this nice photo here. What we see on top is what blood looks like if you extract it from a vein, and on the bottom rows is what blood looks like if you extract it from an artery. So it's pretty easy to discern that they're very different in color. And the only difference here is the amount of oxygen that's contained within the hemoglobin of the red blood cells. So that has a pretty dramatic influence on the color of the light. And using our optical technologies, we can actually quantify and characterize the relative concentrations of these two constituents, and that'll give us a lot of information about not only metabolism but also perfusion and how it varies with different pathological conditions. So here's that concept formalized a bit more technically. There we have the absorption spectra of oxy and deoxyhemoglobin again portrayed here. And we have this nice relationship, the absorbance of hemoglobin or of a different constituent or for a wavelength of light is largely dictated by those two chromophores, oxy and deoxyhemoglobin, and dependent on their extinction coefficients. So if you have the extinction coefficient well characterized, as we do here, and we have a number of different wavelengths as illustrated by these gray vertical lines, you can solve this equation and actually quantify the concentration of oxy and deoxyhemoglobin. From there, you can measure oxygen saturation, which is, for those of you who are in medicine, that's extremely helpful to actually assess the pathological state of a patient or of a specimen. Again, I want to emphasize because of the water window, we like to take advantage of this wavelength region here, where both absorption is minimized by water and also minimized for both oxy and deoxyhemoglobin. So using light within this wavelength region and a little further beyond, you can penetrate deep into tissue and measure these metrics more robustly. Okay, another very important property of light that we take advantage of is the concept of coherence. Like I said before, light has wave-like properties, and so for a coherent light source like a laser that's monochromatic, coherence basically tells you that there's a very well-defined relationship between for the phase of light with the distance that it propagates. So if they all start out in phase, if a bunch of beams of light or a packet of photons of light all start out from this at the same time, as they propagate in space, you're going to maintain this phase with one another, and so you can keep track of that in a very straightforward manner. Most light sources are incoherent, so like an incandescent bulb or the halogen lamp or something. It's more monochromatic, and very quickly there's essentially no relationship with the phase of the many different wavelengths that comprise the broadband light sources that we're accustomed to. In the middle, we have what's called low coherence light, which this is a light source with a relatively low bandwidth of wavelengths. And so if they start out together, there's a certain region over which there will be a well-defined relationship and they will maintain their coherence, but it gets scrambled pretty quickly as it continues to propagate. So this is important because with the concept of coherence, you can take advantage of the principles of interference. If two light sources are in phase together, when they combine, you'll get constructive interference and the intensity of the light will be increased. And you'll also get destructive interference if they're completely out of phase. So there's a whole range of different intensities that you can get based on the relative phase differences between two beams of light. So in terms of Several of the technologies we use, we can use interferometry to measure a sample and compare it to a reference beam, just like an interferometer. That can tell us details about the relative distances that the light has traveled. There's more, but I'll get to that later. One of the first and simplest concepts or technologies that take advantage of coherence is what we call laser speckle contrast imaging. So this very inhomogeneous pattern here is called a speckle pattern. That's what you would get if you projected a laser light beam onto a wall. So several of you have probably seen something like this before. It emerges from the fact that the coherent light that's bouncing off the surface, it's traveling a different length, there's a different path length travel for at every single spot in this image. And so you'll get varying amounts of interference as the light comes back. And so the heterogeneity here is what we refer to as speckle pattern, this sort of blotchy thing. So it actually turns out to be very useful if you just illuminate a coherent light source onto a biological sample with moving scatters underneath, because in addition to the what you get is a variation in the speckle. You got variations or fluctuations in the intensity of several individual pixels here, because they interact with scatters that are moving within the tissue. And so in essence, if you compute a metric called speckle contrast, which is formulated down here, you can actually get a nice relative image or a nice image of the moving scatters within the tissue. So we use it quite frequently for looking at relative blood flow within the brain tissue, but it can also be used for skin or other purposes. Again, just to reiterate, the reason these dark regions in the image are places where there's a relatively high amount of movement of blood scatters, like in an artery or a big vessel. And because there's faster movements, you're going to get greater amounts of speckle contrast, because the speckle fluctuations are happening much faster. Whereas within static tissue, since there's no moving component, there's not going to be much variability at all. And so as a consequence, your speckle contrast will be relatively high. So that's a relatively simple technique to implement and to compute. And so it opens up possibilities to very cheaply and what's the word I'm looking for? You can track relative changes in hemodynamics with simple instrumentation and with very good temporal resolution. Coupling that with the concept that I mentioned before, using optical intrinsic signal imaging, illuminating the brain surface or a biological surface with different wavelengths, it introduces the option of measuring both oxygen saturation with those different wavelengths, using that equation that I showed you before, and also measuring the change in relative blood flow. And coupling those two measurements together, you get a very nice way to compute the metabolic rate of oxygen within biological tissue. The instrumentation is extremely simple here compared to some of the stuff that we work with. It's just you use a laser for the coherent light source for your laser speckle contrast imaging. You can use a broadband light that's filtered at different wavelengths, as was done here, or you could use an array of LEDs so that you can essentially strobe the tissue surface with different wavelengths. All these get detected by different cameras, and so with these very simple computations, you can monitor CMR02 non-invasively and over time for an extended period of time. It's very elegant, very efficient. The trade-off that you make is spatial resolution and the penetration depth that you can achieve with it. So yet another technology. Oh, sorry. Here's a demonstration of of this very simple technology to reveal a very powerful and very insightful observation about stroke pathology. Just using that very simple instrumentation, you can and illuminating this thin skull prep over time after what's called a middle cerebral artery occlusion, inducing a focal ischemia. You can track the CMR02 as it varies with time during the course of this induced stroke. And you can also characterize the prevalence of this phenomenon called peri-infarct depolarizations, which happen somewhat spontaneously and quite frequently over the course of the evolution of the ischemic event. So the blood flow and the CMRO2, correlating those two together will tell you exactly how vulnerable the brain tissue is over time and how it can deteriorate with the progression of the stroke. Here's another, let's see if we can get this working. There's a nice movie here. Okay, well, I'll skip that for now. Essentially, though, using the same technology, the very nice study was done also correlating the, characterizing the prevalence of these ischemic depolarizations and showing how while under ischemia during the course of the stroke, if you induce some sort of functional stimulation, like a Bohr stimulation or a whisker stimulation, you'll induce a greater rate of these ischemic depolarizations, and that'll lead to like a progressive deterioration of the brain tissue, and therefore the ischemic core will evolve and grow, and you'll just make things pathologically much worse. It's a very elegant movie done with very simple technology, so it's unfortunate, but I'll move on. Yet another technology that's made tremendous inroads into actually into the clinic is optical coherence tomography, which also takes advantage of the concept of interference and interferometry, using that what I call the low coherence light source and illuminating a sample such as brain tissue, as done here, I think, and or even the retina. It operates on a very similar principle as ultrasound. You can perform B scans across a sample, measure the prevalence of moving scatters or just scattering in general, and get a very nice non-invasive way of looking at the variation in scatterers within brain tissue, or sorry, within a biological tissue. And what that gives you is initially the raw image that you get, it looks very similar to what you can get with a histology image. They can be easily correlated. But one other feature that people exploit with this coherence phenomenon is the fact that moving scatterers also will induce a Doppler shift in the signal that you detect back. So just like ultrasound, you can use Doppler processing and actually measure the relative speed of the moving scatterers, and that can give you a lot of very helpful information about the hemodynamics within microvessels. All of this is based on intrinsic scattering, so you don't have to introduce any contrast agents. So this angiogram here was taken within I think a 1 by 1 millimeter region of brain tissue, and you can penetrate as deep as 1 to 1.2 or 3 millimeters. So that gives you a very nice, very elegant and simplistic way of getting microvascular angiography within a very small volume without, and also very rapidly. As I mentioned, it's infiltrated the clinic now because it's very non-invasive, very simple, in principle, very simple and cheap to use. So now it's a booming industry for ophthalmology. It's actually $1 billion industry. All right, so moving on. Yeah, I guess I jumped the gun here again. I was talking about using Doppler processing to measure relative velocity within individual microvessels, minimally invasively. Our colleague Vivek, while he was a postdoc here, actually formulated a way to use these measurements and take advantage of the diameter measurements of vessels to actually get quantitative measurements of blood flow within an individual vessel. So that's a very, very powerful technique to actually get absolute quantitation of volumetric flow within individual blood vessels. So there's continue to be a lot of pretty profound developments going on with that. All right, so moving on to yet another light tissue interaction that we take advantage of that's probably constitutes the bulk of the technologies that are dedicated for preclinical methods, is this phenomenon of absorption and subsequent luminescence. So as light propagates within tissue, photons can and are absorbed by the matter that it interacts with, and that results in an energetic excitation of the molecule. So there's a transfer of energy, and hence there's an attenuation in the intensity of the light as it gets absorbed, but continues to propagate through tissue. A downstream effect of this is the concept of a radiative decay. So what I have illustrated here is they're called Jablonski diagrams. This shows the variation in energetic electronic state with the processes of absorption and subsequent fluorescence for a molecule that absorbs and radiates a photon of light. So as it absorbs a photon, the molecule will get excited to a higher electronic state, so higher energy. There'll be some relaxations non-radiatively, mainly given off in the form of heat, and then ultimately there'll be it'll emit a photon of slightly less energy, so there's a longer wavelength here, in the form of either fluorescence or phosphorescence. There's a whole lot going on under the curtain here, but in principle, basically, you shine light with reasonably high energy, you'll be able to detect light with lower energy and longer wavelength. There's important differences between the concepts of fluorescence and phosphorescence. Basically, this additional step here called an intersystem crossing will actually lead to phosphorescence being of an even longer wavelength, hence lower energy, but also takes place on a much different time scale. So this phenomenon, fluorescence, takes place on this time scale of nanoseconds, whereas phosphorescence can occur over the scale of microseconds to milliseconds. And we can take advantage of that in several ways too. Here it is in practice. This is a cuvette filled with a solution of a molecule called fluorescein, which is a very powerful, very strong fluorophore. If you shine it with blue light, you'll be able to very easily detect the green light that gets given off by fluorescence. So this principle is exploited for wide field fluorescence applications and several different laser scanning applications, and also certain forms of endoscopy if you take advantage of the fact that certain tissue constituents also have this fluorescence phenomenon and phosphorescence. It was the concept of fluorescence has been sort of formalized, or it was early on in the 20th century, but over the later half of the century, there's been some very profound developments. The first, and that has introduced the option of being able to image things with very high resolution. I think the most significant one that we've been taking advantage of recently is the concept of nonlinear excitation to photon microscopy, which varies from standard single photon excitation because it requires the simultaneous absorption of two photons of actually higher energy of the one that than the one that gets emitted. There's a lot of quantum phenomenon taking place here that I'll skip over, but involves a virtual electronic state that happens very, very quickly. But in essence, these two photons need to be absorbed simultaneously, and that is a highly improbable event. I think I have the rate equations here. These rate equations describe the rate at which these excitations take place. It's proportional to the number of molecules in the ground state, that being the state here, the photon flux, and also the what we call the absorption cross-section. So two photon microscopy is one of many forms of nonlinear optics, and that basically just describes the fact that the rate is proportional to this, not directly proportional to the flux, but proportional to a higher power than flux. It's not linear, it's actually quadratic in this case. Another important feature is the fact that these cross sections for both single and two photon are drastically different by many orders of magnitude. So what that means is that this phenomenon that you want to elicit, this simultaneous absorption, it's extremely unlikely. And if you want to actually make it happen with regularity, you need to essentially bombard your sample with very high photon flux. What that breaks down to is depicted here. Because it's such an improbable event, you can only induce it using the right light sources that deliver tremendous amounts of power, and then using an objective lens that can focus the light down to an extremely tight focus. That's the only way that you're going to be able to get a sufficiently high concentration of photons to induce this effect. What that does is actually give you, for microscopy purposes, that localizes the amount of light that you're going to, or that localizes the region at which you're going to induce fluorescence, and therefore it introduces the ability to get very high axial sectioning in your image. So this phenomenon, well, I'd be remiss if I didn't mention first that previously, in the 1950s, there was a high resolution method formulated called confocal imaging, which relies on the single photon excitation phenomenon. But what happens is you the way that it's, you get this high resolution is that you filter out a lot of the stray light that gets excited, and only your detector will only be able to see light from the focus region that you want. That's done with spatial filters introduced in your detection path. It's been very helpful. It's still a workhorse for various biological applications, but it's simplistically, technologically, it's cheaper in some ways, but I would argue that the two-photon excitation, multi-photon, is superior in terms of the advantages and capabilities that it offers. Most non-trivial of which is the fact that you're using, since you're using near-infrared light to induce this effect, you can actually penetrate deeper into thick tissues, turbid tissues, and so this introduces the ability to measure deep within the cortex of small animals, or up to 1 millimeter within turbid biological tissue. Both are profoundly useful. Both are really extraordinarily helpful, but there are pronounced differences as well. This is a nice illustration showing you the improved axial sectioning that you can get from laser scanning on microscopy. A normal wide field fluorescence source where you're using just you're not scanning across the sample, you're illuminating the entire tissue at one time using normal objective lens. Your focal spot is actually going to be quite broad in the Z direction over the entire sample. So the image that you focus on actually, or the tissue region that you focus on is actually a lot thicker than the region that you can focus on with laser scanning microscopy methods. What that boils down to is nicely depicted here. This is confocal image compared to a wide field image, and it's, I'm assuming I don't have to explain that, you get a much crisper and nicer, sharper image here. Another very important feature that this illustrates is the fact that with fluorescence imaging or phosphorescence imaging, it also offers a lot of versatility in terms of the number of different constituents that you can label, because there's all these developments taking place where you can target specific organelles or cell constituents or even cell types. You can excite different ones of these fluorophores in the same field of view, and overlay them and get this nice, more comprehensive image. Two-photon excitation actually introduces the ability to measure them simultaneously if you combine your contrast agents correctly, and so that should give you well, it paints a more detailed picture literally, because you can image multiple fluorophores at once, and also you can characterize their relative interactions over the course of time. So it gives you a lot of information about the kinetics and prevalence of different constituents simultaneously over time, minimally invasively. Importantly, so what I just showed you were intensity-based fluorescence images, and that obviously is tremendously useful for different applications. But moving the capabilities further, we take advantage of the rate at which these fluorescence phenomena take place as well. So in our lab, we make use of more sophisticated electronic hardware that allows you to measure the time resolve profile of both fluorescence and phosphorescence. And using some post-processing, you can fit these to using nonlinear fitting or other analysis techniques. In essence, you can break down the fluorescence in terms of the sum of different constituents with different fluorescence lifetimes. What that gives you is it'll allow you to interrogate the microenvironmental conditions with greater specificity, and give you more information in general. You can investigate different features of temperature and viscosity. In our lab for brain imaging, we use it a lot for being able to actually quantify oxygen tension. And in my case, I've done a lot of work looking at the intrinsic fluorescence of the NADH, that's a constituent in the mitochondria, so you can get a lot of information about metabolism. We've coupled all these different modalities together into a multimodal system, trying to get even more information out of a given sample, for in vivo imaging. So putting them all together, we can get information about cerebral metabolic rate of oxygen on a microscopic level. Real quickly, this is a nice illustration of the multimodal imaging that we can achieve. Laser spectral contrast imaging can give us, tell us the spatial variation of cerebral blood flow in a cranial window. So after a focal occlusion, we see that there's pretty much minimal blood flow in the infarcted region. Conversely, if you look at the NADH lifetime, you'll see that there's a much greater intensity of NADH here, illustrating that there's the tissue is metabolically starved for oxygen, and it's also reflected in the lifetime. One last feature is being able to measure PO2, that's oxygen tension in the vessels and in the tissue. Simultaneously measuring that and cerebral blood flow using OCT, we can get a lot of comprehensive information about microvascular hemodynamics and oxygen delivery. So this is an example in an awake animal of PO2 during and after functional stimulation. I think this was a whisker stimulus. And we see pretty pronounced variations in the kinetics for both arteries and venules. So that's a work in progress right now. I think I've gone over. So there's a whole, I've gone over, but still I've managed to leave out a tremendous number of different applications. There's just not enough time to go over these, but this is basically the cutting edge of preclinical methods right now. I encourage you all to look further, but at this point, I think I'll just hand things over to my tag team partner, and he'll talk about translational methods.
Well, thanks for holding on. And let's see if I can do an accelerated version of the rest of my talk. Abbas gave a great introduction to a lot of aspects of biomedical optics and tissue optics, so it will actually allow me to skip some of the details I'm showing. In any case, I wanted to present this slide and put into context the technology that I'm going to talk about, which is diffuse optics. So optical imaging domains are very broad, and this scale is, actually this should be M, not capital M. So this is the depth at which you can image and the resolution with which you can image. So Abbas has talked a lot about this area, and I'm actually going to go to the other end where you are able to actually image in vivo in an adult or image. I'm actually going to show imaging examples too. Sometimes it's just quantification of physiology. And that allows you to actually do a study in a patient or in vivo. And what's key for it is using near and infrared light. So this picture of me holding a flashlight against my hand and against my cheek, and this flashlight was white. So what does it mean that now you can see only red light? It means that the red light actually managed to go further and the rest was stopped. So as I was saying, Abbas has already kind of given you an idea of how light interacts with tissue, and the only thing I want to add is that at this wavelength, the scattering is much more intense than the absorption. So we use these terms called absorption and scattering coefficients, which are basically inversely proportional to how far a photon will travel on average before it encounters an absorption or a scattering event. And while it's actually quite possible for a photon to travel 5 to 10 centimeters before it gets absorbed in tissue, it will change direction every 100 microns. So its initial direction is very quickly lost, and this starts resembling a diffusion process. The best way I can think of explaining how to visualize it is drop of ink in water and watch how it spreads out. So the light does the same thing, except much faster. And again, reviewing something that Abbas mentioned, there are two important tissue constituents that luckily also drive the optical measurements in the infrared. So I'm assuming most of you really know about hemoglobin and how it carries oxygen. And luckily, the hemoglobin with oxygen has quite a different absorption than hemoglobin without oxygen. So even by taking measurements at two different wavelengths of light, we can actually quantify them distinctly. And then the sum of them is proportional to the total amount of blood in tissue. And the ratio of oxygen to total is the hemoglobin saturation, which is important because it tells us how much oxygen the tissue is extracting. And as far as scattering, it actually has this monotonous decrease with wavelength. And as I would like to say sometimes, this is part of the reason why the sky is blue. because scattering is much higher in the blue region. And the parameter that we can measure that is relevant to diagnosis perhaps is the power with which scattering depends on wavelength. Because very tiny particles will actually have minus fourth power. That's Rayleigh scattering. And as I was mentioning, the way we model light propagation is, yeah, go ahead.
So, I mean, this paper is often this quantification of bio-oxygen saturations. We also have this water spectrum kind of creeping in.
Yes.
So what wavelengths are typically used? I feel like, you know, there's like the Grinwald Malonic paper, like back in the day.
Well, no, so that is true. I mean, the best way to typical wavelengths are, there is this crossover here of the so-called isosbestic point where the two have the same absorption. So, or specific absorption. So usually you have a wavelength below and one above for mathematical inversion purposes. So that doesn't imply you have to assume a water concentration. And if you're doing cerebral measurements, the percentage of water in tissue is not that, doesn't vary that much. So you can make perhaps an assumption. If you're measuring other parts of tissue, you're right, you should really have an idea how much water you have. So you know, at a minimum, you need another wavelength, preferably above 800 something nanometers. And it's kind of going from there. So in a research setting, the most, you know, complete technique is taking the complete spectrum with a light source that has, you know, it's broadband. For imaging instruments, and I'm going to get into it later, I guess, it's perhaps having several wavelengths is already better. So I'm just putting this up to, you know, mention that the standard approach for modeling, you know, particle propagation and transfer is a radiative transport equation that quantifies the transport of light along a certain direction at a certain location over time, and it's essentially an energy balance of light coming into your propagation direction and being scattered away from it or absorbed. As I was saying, the direction that the photon started traveling in is lost very quickly in tissue. So unless you're trying to make measurements very close to the point of light injection, you actually can assume that light is propagating homogeneously, in which case, by integrating over 4 pi these equations, you actually remove the angular dependence and you end up with the diffusion equation. Basically, equations that are first order in time and second order in space are diffusion equations. It applies to heat diffusion as well, also particle diffusion. And so we can use this to model light diffusion. And we have simple solutions for it. And before I go into details of the instruments, I also want to briefly review the building blocks for it. Now, most of what we do, especially for the tissue measurements, are boxes in which we put sources of light and detectors and some kind of electronics to, you know, power them and collect the data. So I want to briefly go over these light sources and light detectors and also how we move the light around. So as I was saying, you know, one of the simplest sources of light is a lamp. And there are scientific lamps with specific, you know, well-characterized spectra that cover the entire region we care about. And some examples looks like this. Is basically the size of my hand. More recently, LEDs have really become really useful because they've been available with high powers and they're very inexpensive. So for portable systems or where, you know, you don't need the best spectral purity, LEDs are a good choice. Laser diodes have actually been in use for longer because the advantage is that they have some coherence. The light is much easier to couple into an optical fiber, but however, they are more expensive and more delicate. It's very easy to burn them, as most of us experienced in the lab. And then there are all sorts of laser systems. So when I say laser system, it can be anywhere from a laser diode put in a cavity, paired with the external cavity to stabilize it, or you can have all sorts of laser systems, and they can vary from the size of, you know, still battery to a tabletop system that can emit femtosecond pulses and emit into watts of power and so on. On the detection side, the workhorse is the lowly photodiode, and its inverse conduction depends on the light intensity, and that could be good enough for many applications. If you need higher signal, you can use what's called an avalanche photodiode, where there is this there's a reverse bias, and when a charge is generated by a photon absorption, it actually propagates into a cascade and generates an avalanche. So basically, it's a signal multiplication, and it basically has high internal gain. It's very sensitive, and again, it can more easily be damaged, and it's more expensive. And then this is a little bit of a relic that's still used. It's called the photon multiplier tube. So it's actually a vacuum tube. I don't know when was the last time you've seen a vacuum tube, but it has the same principle of creating a cascade of events where this charge accumulating, and you can achieve even higher sensitivities than avalanche photodiodes. The one issue is that the silicon devices can work up to about 1,000 nanometers, but most photomultiplier tubes are not very good beyond 800 something. So it depends what you're trying to measure. And also these guys can very easily be damaged. And they're sensitive to magnetic fields. So if you're trying to make an instrument that comes near an MRI scanner, this is not the best choice. And on the detection side, we should also mention cameras, because essentially cameras are a collection of light detectors. I mean, CMOS cameras are a collection of silicon photodiodes. And there used to be really, the charge coupled device, CCD sensors were widespread, but now become very niche because there's only very few applications where they actually are still superior to silicon-based technology. And a camera, besides giving you an image, can be used to obtain, to some extent, even high rate acquisitions, or some cameras can have built-in electron multiplication gain, and which can be modulated very fast to create a heterodyne system and so on. So it depends on the application. And last but not least, this is how we move light around most of the time. So it is certainly possible to build a system that's in contact with tissue, and sometimes that makes sense. But also one of the big advantages of optical measurements is that you just need a fiber to deliver light and some fibers to collect light, and you can stick them in wherever you want, most often together with some other medical imaging. And the main principle of light propagation in a fiber is that the fiber is a concentric structure with a rod in the center, followed by a sheath that has higher refractive index. So the light gets trapped, lower refractive index. So the light gets trapped through total internal reflection. And there's more than one variety with step index or gradient index that have mostly become important when you're trying to propagate short pulses. And since sometimes we want a large collection area, if you try to make a 2 millimeter glass fiber, it's essentially a rod. It cannot be bent. So the alternative is to make a bundle of tiny fibers, which may not be 100% efficient because some of the areas are active, but allows us to capture light over an area. So sometimes we're trying to capture light that's been attenuated 1 million times or more. So sometimes we do also have to take the area to take advantage of a larger collection area. So that being said, there's a few typical technologies we use. So the simplest measurement is measuring the intensity change as light travels to tissue. And this is a simulation of light propagation where light was injected at this location. This is actually a human head. This structure here is the cortex. This is derived from an MRI scan. And then we generally collect light some distance away. Sometimes, it's usually several centimeters. And this plot is not how the light travels, because light travels everywhere, but this is the path of the photons that entered here and came out here. And then this is the sensitivity profile in the sense that this is the partial derivative of the signal of the detector with respect to a change in any of these locations. So this is, as you expect, the light, the most strongest sensitivity is near the source and also quite strong near the detector. And this is what we call the photon banana. So the depth of this is about 1/3 to 1/2 of the actual distance between the source and detector. So for an adult head, it will reach the cortex to some extent, but not very deeply, but enough to actually take a measurement. So this is most commonly used for functional measurement, which I will come back to later, but that's a canonical response of a neural activation where you have an increase in blood flow, but that's not directly visible there, but the result of it is an increase in oxyhemoglobin and decrease in deoxy. So that's the red and the blue curves, and then usually correlates with the stimulation. So for this is enough to measure intensity, The problem with intensity is it could be a result of changes in absorption or scattering. So you cannot distinguish them, but sometimes this change in scattering is not significant. So you can make the assumption that scattering is constant and assume that all the change is absorption, and that's good enough for many applications. If that's not good enough, then instead of injecting a constant intensity light, you can modulate the light coming in and create what's called a photon density wave, essentially. So you have both amplitude and phase differences to measure. In that case, you have two unknowns and two variables, so that you can obtain absolute optical properties. Well, at least the average optical properties under your probe. And the sum that I'm showing below is just a solution to the diffusion equation for each case. And the final method that contains the most possible information is injecting a short pulse of light. And this is sort of an animation of the photons traveling. And this, for those of you who understand Fourier transforms, essentially contains many frequencies. Not all of them, because it's not a delta pulse, but this contains even more information than a frequency domain like I showed before. Of course, instrumentation gets progressively more expensive and bigger in size as you get this information. One advantage of this, however, is that the optical properties are defined from the shape of the curve. The actual height of it doesn't matter anymore. So this is an advantage if there is any chance that your fibers might move, and then if the contact changes, the amplitude will change, which will impact the previous methods. But here, as long as you're not trying to measure through that change, the absorption tends to depend on the slope of the temporal slope of the light pulse coming out, and the scattering depends on where the peak lands versus when the laser fired. So there's some advantages to this. And finally, technique actually I think is very useful and complementary to all of this is called diffuse correlation spectroscopy. So Abbas went into some detail about laser spectral contrast imaging, and the physics is exactly the same. It's watching the speckle pattern on tissue as tissue components move around. And again, we get lucky here. While hemoglobin has been absorbed near infrared, the main scattering particle that influences the signal in near infrared influences the speckle fluctuation is the red blood cell. So we can track blood flow with this. And this is a model that essentially is similar to the propagation of light for the absorption-based measurements, except there's this dynamic absorption term that depends on the amount of particle motion. So from this particle motion, we can derive the blood flow. And the measurement in this case is a little bit more complicated because what we have is these fluctuations and they have a frequency spectrum. But because we need to look at we actually need to capture the interference speckles. At least the standard approach to this is to use what's called a single mode fiber, which can only propagate one electromagnetic mode and is essentially monitoring a single speckle. That also means it's 5 microns in diameter, so you're capturing a lot less light. So you're actually only getting a photon once in a while. We actually use photon counting detectors. So it's easier to process the signal in the time domain and look at the intensity autocorrelation curve. So this is what this plot is. The x-axis is time, the y-axis is correlation. And it's a little bit hard to see, but this is 10 to the minus 6. So the way I like to explain this is that over a microsecond, the light is steady. So that's why it correlates with itself. But I mean, autocorrelation means you take a signal and you slide it along itself and compute the dot product of the overlapping region, more or less. Now, if we look at the 10 to the minus 3 millisecond, the correlation goes down to the baseline. So therefore, the light intensity is basically random over intervals of a millisecond. And then it transitions in between. So the transition actually gives us information about the amount of motion and hence about blood flow. And what's really can be powerful is putting these two together. So with the near-infrared spectroscopy techniques, we can measure how much oxygen gets extracted from the tissue as it passes through a capillary. And with diffuse correlation spectroscopy, we can measure how much the blood flow has changed. And then if you multiply these changes in a relative fashion, you can get changes in the rate that oxygen is consumed by tissue. So the advantage of this is that that's actually a fundamental tissue property. Hemoglobin concentration and blood flow, they are kind of tools that tissue is using to feed itself, but oxygen is the actual food. So it tells you a lot more about the physiology. And there's, at this point, many commercial devices as well in this field. Most of it is based on the intensity measurements. This kind of stuff is actually in operating rooms to measure cerebral oximetry, as in hemoglobin oxygenation in the brain. The issue is that it makes a lot of assumptions, as I was trying to mention earlier. So they don't work that well. Honestly, they work well enough that the hospitals have bought them, but not well enough that they use them much. So they generally stay unused, except for the occasional surgeon which would like to use them. So we hope to do better with our research. And then these are devices that actually people use for functional measurements, and I'll briefly come back to this later. And this is the only, this company, ISS, is the only one that makes a commercial device that's using the frequency modulated approach. And then Hamamatsu in Japan is, I think, the only, they were the only company to make a time result, with a pulse light spectrometer. Now there is something called the Baby Lux project in Europe that's combining time domain and diffuse correlation spectroscopy for baby measurements. So I'll try to briefly go over some examples because I technically have 5 minutes left. So I'm starting with breast cancer imaging because that's what I did as I started at the Martinos Center. So here is an example of us sticking fibers in a place where they don't necessarily belong, but we hope they can be useful. So this is an X-ray mammography machine on the left. It's actually what's called digital breast tomosynthesis, in the sense that the X-ray tube can actually tilt sideways and give a partial angle CT scan, essentially. This is an instrumentation tower which contains a lot of light sources and detectors. The bottom is actually intensity measurements. The top part can also do phase measurements, so it's combined because it's prohibitively, well, it's not just the expanse, but also the speed. If you measure only intensity, you can measure much faster. So we have a hybrid approach where we get some information on the absolute properties, maybe once every few seconds, but then we interpolate using the intensity measurements for up to 25 times a second if necessary. And we integrate these fibers into the compression plate of the machine. So there's this section here contains the X-ray detector, and this is a plastic plate that can go up and down to compress the patient's breast. And then we put the fibers in between. This version included actually plastic fibers, so we can get the X-ray through them. Turned out the plastic was a bit degraded by the X-ray, so I think we need to iterate, and for now we replace them with glass fibers, so we can no longer take the image simultaneously, but this is the hope that we can take them. If this is where to be used, it would actually be a simultaneous acquisition of both methods, a little bit like PET-CT in a way, if you're familiar with that. And well, we wrapped it up in something that looks nicer because this is actually installed at the breast imaging division at MGH, the main campus. This is the system diagram. As I was mentioning, I'm not going to go into details, but it contains 32 sources that are intensity-only measurements, and then up to 20 locations where the amplitude and phase can be measured. Something very neat about this system is that it's using a very high-speed analog to digital converter, so it can sample the full signal. We're using 100 megahertz modulation for these frequency domain methods because that's kind of a Goldilocks frequency where the phase change is high enough to be measurable, but the frequency is not so high that the detectors start to become a problem. But the typical approach for demodulation of signals, was in the past analog with what's called heterodyne, which I don't think I have time to go in. But this is the brute force, everything, the best case approach. We just digitize the entire signal, a full sampling rate, and we can do any processing to it afterwards as we wish. So it actually reduces the noise level of the system quite a bit. And this was a way to test it. This is jeweler's wax, which both melts and dissolves in water, which was interesting because we cast these balls in a silicone mold, and then we put them through the wall of this container and then poured silicone rubber, that is typical phantom for us, around them. And then we drew the metal tubes and then pumped in hot water to dissolve it. So we ended up with what we call a phantom that has cavities with tubes attached to them, and we can propagate solutions of ink and milk, or ink and something called intralipid, that's lipid suspension, which simulate optical properties that kind of like tissue. And the advantage of just having simple cavities is that they represent accurately if you have an object inside. We try to put some glass spheres, for example, first, but the problem is the glass wall itself conducts the light so well that it actually caused apparent negative absorption. So, and this is an example of the image we get with that. The cavities were different sizes, so you get different size inclusions. And if we actually pumped, we change the concentration of ink inside it, the absorption changes as well. One of the downsides of this so-called diffuse optical tomography is you only get partial contrast recovery, so the change in concentration was higher than the concentration we come out, but the way we use this technique is to look at the relative changes. So this is a breast image where 2 centimeter invasive cancer, I think 2 point something centimeters maybe. And the typical signature is there is more blood in the tumor area. It does kind of expand beyond that. It's actually, some people published, a couple of groups looked at this and published that the influence of a tumor extends a little bit beyond its boundary. So in a way, the optical technique can actually be more sensitive because the region impacted is higher. And then this is unique to our project, that because we're doing this together with mammography, the compression actually changes the amount of blood in tissue. And this image shows the change in blood volume as you compress from half to full mammography compression. And what happened is the tumor lost more blood than the rest of the tissue around it. And this is an example of watching a patient respond to chemotherapy. The top row is the baseline image where the bluishness is essentially what I just showed before. This is the change in blood volume as you compress further from half to full. The next slide, the next column is when you go back to half compression. And we expect this to be complementary. We want to make sure that's the case. And then this is the X-ray image showing the tumor. That's the original size. It was quite large. And then for this patient that was not actually a complete responder, late in the treatment, there was still this feature of blue that turns into red in normal tissue. In this, where the tumor was, while the normal tissue kind of behaved the opposite way. So this tells us there's still a residual disease. It's not just scar tissue. And it turned out that pathology that there was still, I don't know, I think it went from 4 centimeters to 7 millimeters, but it's not fully gone. So the idea is for optical imaging to guide chemotherapy by actually monitoring the change in the tumor during the treatment. So now switching gears a bit to the neuro side. I did want to mention functional nears because some of you are probably familiar with functional MRI since we're in Martinos, and the basic biophysics of it actually are linked in that functional MRI, as most of you probably know, is driven by deoxyhemoglobin because it's paramagnetic, and with optical imaging we can measure deoxyhemoglobin as well. This is really, this is probably almost 20 years ago now. This is one of the early measurements of the neurovascular coupling effect on the near signal. And this is purely the signal intensity. This I think was I think this was electrical stimulation. And what you see is the signal going down because there's blood coming in. And this is the, I guess, canonical response for optical measurement. Several kind of stimulations result always in some increase in oxyhemoglobin, decrease in deoxyhemoglobin that reverses after the stimulus goes away. And depending on the nature of the stimulation, the response may be ipsilateral or contralateral. I think this is all contralateral. So this just shows that the technique is not just noise because you actually see a bigger response on the side you expect to see it. And then, this is work done maybe now 12 years ago on validating the FNIR signal with fMRI. And there was this vitamin E capsules put on optical fibers. And to be honest, I'm not sure what stimulation paradigm this was, but this is showing that the optical reconstruction overlaps quite well with the fMRI activation area. And if you look at the temporal response, this is almost amazing how well bold and HBR are anti-correlated. I mean, as you know, the bold signal is essentially, if you take the image intensity, the more deoxyhemoglobin you have, the quicker, the shorter T2 star and the quicker the image decays. Therefore, reductions in deoxy result in increasing bold signal. So as you can see, temporally, they're very well aligned and the mirror image of each other. And I think this is normalized and inverted to show this even better. And beyond that, I guess this is the hot topic in the neuroimaging field, this restricted state functional connectivity, and you can do the same thing with optical measurement. This is a few examples of validation studies that show that you can do these measurements of FNIRs, and an example of how you could actually quantify this. This is looking at the pediatric, changes in neonates as they get older, and how the connectivity pattern changes. So essentially, a lot of the studies that can be done with fMRI can also be done with FNIRs. The advantage being that optical can be done in it can even be, ambulatory. At the very least, you don't have to go in a scanner. So it's more suitable for, people that are sick or people that are, or kids that don't want to stay still. And the kind of the future is this, that you have with wearable systems that just have a little electronics control unit, and otherwise there's just on the head, and you could have a person walk through the city. There was actually a study where they let people just walk through London and monitor their brain patterns and try to guess, whether they saw something interesting or not. So that being said, there's the other area that our group has been working on a lot is brain health monitoring. So it's a little bit different than functional measurements because now we're not looking at stimulus-based paradigms, but we're looking at the absolute situation with respect to oxygenation and blood flow. So very briefly, surgeries under bypass especially lead to a lot of cognitive deficits that generally resolve, but it still impacts people's life on a period of weeks to months. And one of the hypotheses is that the brain oxygenation, the supply of oxygen to the brain is impaired because under anesthesia, the blood pressure is usually reduced, and there is this mechanism of auto-regulation that's supposed to hold the blood flow constant, but it actually can change when somebody's sick. So there is no current clinical technique for monitoring blood flow for long periods of time. There is transcranial Doppler ultrasound, but it generally cannot be done for long periods, and it's very sensitive to motion. While optical measurements with this fiber optic probes, you can just tape it to the head and it will stay in place for a long time. And this is a diagram of the instrumentation we use for this study, which just combines the near-infrared spectroscopy with DCS in one box. It looks like this, essentially. And the software interface can give us a real-time indication of both oxygenation and blood flow. This is a typical maneuver we show for as an example where you inflate a cuff around your arm and measure the forearm. And you can see how the blood flow decreased when we inflated the cuff, and then the saturation started going down because there's no more arterial blood coming in. And then when you release the cuff, there's a sudden jump in blood flow, and of course saturation comes back too. This is one way it can look in the clinic. We used to glue the probes to the head. Now we actually stopped doing that because the glue seems to, actually not the glue, but the solution used to remove it. I'll back up one moment. This is the kind of glue they use for EEG, it's called collodion. So the collodion remover, however, degrades our optical fiber probes, unfortunately. So we end up tying some kind of bandage to hold it in place. But this is actually in an operating room at MGH, and this is the instrumentation tower, and this is what the optical probe looks like. And we just affix to the head and monitor through the entire surgery. And this is the kind of information you can get. That's a lot of things happening, so we're still digesting what this is telling us. But a couple of features that are kind of obvious is, when people are moved on bypass, their blood is essentially thinned to reduce the chance of clotting. So you see this sudden drop in total hemoglobin concentration when they go on bypass, and then it goes back up, at least partially, as they come off bypass later. And then this is blood flow, and this is oxygen consumption. They are fairly tightly related. Most of the change in oxygen consumption has to do with temperature because chemical reactions depend on temperature, and the patients are cooled during the surgery. So as you see this progressive increase is because there is a progressive increase in temperature. And where our main concern is not having enough flow, but actually having too much is bad too, because it could cause things to come off the vessel walls and cause microstrokes and the like. And really, the dangerous points are where the flow has to stop, and depending on the maneuvers they have to do. So the saturation measurements are basically what's done clinically now. The problem is this is a lagging indicator. So blood flow changes first and then saturation. So by measuring blood flow, we can earlier see that something is wrong. And for now, here's a couple of examples of things that were kind of unusual that we saw. Here is the green trace is the blood pressure, and we see the signal is actually oscillating with it, which you don't really expect because the auto-regulation is supposed to actually stabilize blood flow. And these are slow oscillations. I mean, period is a couple of minutes, so it's not like it's a few hertz. That auto-regulation cannot do, but over minutes it should be able to. So this was definitely a problem. That was a sign of impaired auto-regulation, and you can see the correlation only during the bypass period. This guy, or actually, I don't remember what gender it was, and that the subject was, but this time the blue trace here is a very short separation measurement, so it's primarily telling us what the skin is doing, while the yellow and red are longer distances, and it also monitors blood flow in the brain. So we see only the longer distances oscillating this time. And if we take a periodogram, a spectrogram, I mean, we see that this frequency band only shows up in the longer distance during the bypass. And where these oscillations come from, it's also unknown, but it's again not a sign of unstable physiology. So this is, I guess, where we are now. The goal is to correlate any of this information with the outcome of the patient, which can be quantified as, you know, the cognitive scores or the number of days they spend in the hospital and so on, and then see if there is any signs that actually warrant intervention. Because the anesthesiologist uses a combination of medication and inhaled gases and other methods to control the body physiology. And it can be a quite complex mechanism, so it's not so clear. For example, if it's given, they might give a vasoconstrictor to increase blood pressure, which you would think would increase blood flow in the brain. But what if it causes vasoconstriction to the extent that the increase in blood pressure cannot overcome the increased vascular resistance? You could actually end up with less blood flow. So this is where you really want to be able to monitor it in real time. So with that, I think I want to say thank you. This is a slightly old picture of the optics group, but actually pretty representative of the work you've been seeing. And let me know if you have questions.